Welcome back to another problem. Let's get right into it. So, the ladder's base rotates about the z-axis through point P with a constant angular velocity. Simultaneously, the ladder pitches upward at a constant rate of phi dot is equal to pi over 30 radians per second. And the second portion of the ladder, xy, extends outward at a constant rate of 0.25 meters per second. At some specific time t, where phi is equal to 25 degrees, px is 10 meters, and xy is 3 meters, determine the magnitudes of both velocity and acceleration at this time t. Okay, so in a problem like this, I think the first thing that you're going to want to do is decide on your coordinate system. So far we've talked about rectangular, or as far as 3D is concerned, rectangular coordinates, so x, y, and z, cylindrical coordinates, which is r, theta, and z, and then we have polar coordinates, which is big R, theta, and phi, which is your rotation about the xy, or about the z-axis, and then your pitch angle phi. And I mean, this problem, I think, is screaming to use polar coordinates, since we are given information here about theta and phi, as well as we have something that resembles the r-axis. So I think using polar coordinates is it would be a very good idea in this problem. And I've already gone ahead and written out the governing equations for polar coordinates for v and for velocity and acceleration. And so all we have to do as the problem solver is we need to populate the different velocity and acceleration components along the radial direction, the theta, and the phi directions. And so let's get right into it. I'll pull up my little box and reorient the screen, and let's begin. So because we're essentially just looking to populate those equations, I think it's really helpful to list out our knowns so we have them ahead of time. So first things first, we are given the angular velocity, omega, and we'll just call this theta dot, just to match our convention. And we're giving that is pi over 20 radians per second. Okay? We're also giving the pitch rate, phi dot, which is pi over 30 radians per second. Okay? Now, we're given the velocity of the portion xy, but nothing about px. So if we can imagine starting our origin, say right around here at the base, and we have this radial vector that will extend outward, maybe draw that in, we can say that our position, or where our guy or little dude will be at when he's trying to save this cat from the tree, his position is going to be dictated by how far xy is extended at some time t plus the constant px. So we're saying px does not change in this problem. And so by doing that, we can write that r is going to be equal to px plus xy. Okay. And then, so what exactly is that position going to be? Well, we're given essentially xy dot. So really what we could write is r is equal to px plus xy dot times some t. Okay? We don't really know what t is, but it doesn't really matter because we're given all the information we need. And you'll see that in a second. And so then consequently, if we took a derivative of this and we got r dot, then that would just mean that r dot is equal to the time rate derivative of px is just 0. So we'll have 0 plus, and then we'll get rid of the t whenever we differentiate. And so we'll have xy dot, which is just going to be equal to that 0.25 meters per second. Okay. And now you might be wondering why I didn't use the product rule on xy dot times t And it's just not really necessary because I was really just writing that as a way to make it more clear where our radial direction was coming from. It would be erroneous to apply or you could go ahead and apply the product rule, but you would see that you get the same thing anyway because xy double dot is just 0. So maybe I'll do that real quick just to be a little bit more clear. So if we did xy dot t and then we did d over dt, this would just be xy double dot t plus xy dot times 1. But xy double dot is 0. So we would get the same thing anyway. Okay? Almost done running out our knowns. And then at whatever time t we're looking at, we have phi is equal to 25 degrees. Px is equal to 10 meters. And then xy is equal to 3 meters. And so then consequently that makes r, which is equal to px plus xy, 13. All right, cool. Now we can move along with the problem. So I'll just reorient the page. Okay. Let's go ahead and get our velocity down first. So we know that our velocity has 3 components, one in the radial direction, one for theta, and one for phi. And the equations here are below. So just given what we know already, we just calculated r dot, or we were given r dot, excuse me. We know theta dot, they gave that to us. We know phi, they gave that to us as well. We also know phi dot, and we just calculated r. So this is pretty simple. It's just going to be a plug and chug right now. And so if we go ahead and do that, we know r dot is equal to 0.25 meters per second, that's just going to be VR. V theta is going to be r theta dot cosine phi. And if we plug in our givens from over there, we'll just see that this is approximately 1.85 meters per second. And then if we go ahead and calculate V phi, which is just going to be r phi dot, we'll see that this comes out to be 1.36 meters per second. Cool. Now, final step. They wanted the magnitude of velocity. So if I do the norm, that's going to be VR squared plus V theta squared plus V phi squared. Take the square root of that. And so if we plug in our values for r dot, V theta, and V phi, we'll see that this is approximately 2.31 meters per second. Box that guy up. Okay, simple enough. Once we just kind of clarified our problem and wrote out our givens, we see it was just a simple plug and chug. So I'll get rid of that box, just draw a line, separate, and we'll move on. Okay. Now for the acceleration. This is where things will probably get a little bit more interesting. So we are given our equations for the different components of acceleration in the r, theta, and phi directions. And they look kind of complex. There's a derivative in the theta and phi terms. But, don't let that scare you. It's just calculus. We'll just have to be diligent and careful with our terms as we take derivatives and proceed carefully, and all should work out fine. So we will do just that. Let's look at the radial direction first. So we have AR, hopefully I copy this down right again, R phi dot squared minus r theta dot squared cosine squared phi. Okay. Well, if we look back here at our givens, we see that r dot is actually constant. We know that this portion that our little guy is standing on to save the cat from the tree, the rate at which that is extending outwards is constant. So if we took another time rate derivative, it would just come out to be 0. The acceleration of xy is 0. So therefore, we know r dot is 0, right? Okay. Now, we can maybe just try and simplify this a little bit more. We can pull out let's see here. We can pull out the minus r, and then we're left with a phi dot squared. That's going to be plus a theta dot squared cosine squared phi. And then if you even wanted to, you could make that just a little cleaner if that cosine squared looks weird to you. Oh, not theta. Phi dot squared. You could do that squared if you want. You remember your exponent rules. You don't want to square the entire term because then that wouldn't be the same thing. So just the theta dot times cosine phi squared is acceptable. Right? And then, we were given phi dot, we're given theta dot, and we were given phi. And we calculated r as being 13 meters. So if we just plug in those values, we'll see that r is negative 0.406 meters per second squared. Okay? There's one value done. Let's move on to a theta. And from before, we know that the value, or the equation for that, is going to be cosine phi over r times d over dt of r squared theta dot minus 2r theta dot phi dot sine phi. Okay. Now, whenever you're dealing with equations like this and you have a lot of terms, I can't recommend it enough. Don't plug in values until the end. Keep everything symbolic because you never know what's going to cancel out, and I really just think it eliminates the potential for additional mistakes. So I will do that here. So if we simplify this a bit, we have cosine phi over r, and we have to take the time rate derivative of r squared theta dot. So doing the product rule, we'll have 2r r dot theta dot plus r squared theta double dot. Okay? And then we'll just have this term over here on the right that we haven't used yet. And there we go. But what do we know about theta double dot? Well, from before, or actually I'll leave that box here and just zoom in. We know that the angular velocity is constant. Everyone see that there? We have this constant. And so that means that theta double dot is 0, right? And so now we just have a theta is cosine phi over r times 2r r double dot theta dot, or I think I said double dot, it's just r dot, minus 2r theta dot phi dot sine phi. These r's are going to cancel out. A theta is just going to be equal to cosine phi. I'll bring the 2 out in front. R dot theta dot minus 2r theta dot phi dot sine phi. And now it's just plug and chug. If you plug in the values from above, if I did my math correctly, See, it's negative 0.1096 meters per second squared. Good deal. On to the last one. So we got A phi. All right, copying down our equation from above, we have 1 over r times d over dt of r squared phi dot plus r theta dot squared sine phi cosine phi. Okay, doing our product rule again, we'll see that this is going to be 2r r dot theta dot plus r squared theta double dot, or phi double dot, plus r theta dot squared, and so on. Again, that pitch rate, phi dot, is constant in this problem, which we're given as pi over 30 radians per second. Therefore, similar to the acceleration in the theta direction, that phi double dot term is going to be 0. So we can just write a phi, and I can already see that these r's are going to cancel out again. We're just going to have 2r dot phi dot r theta double dot squared sine phi cosine phi. And so if we just plug in those values again, plug and chug, we see a phi is going to be positive 0.175 meters per second squared. Okay, then if we just combine all these, we know our magnitude of the acceleration is going to be ar squared plus a theta squared plus a phi squared all square root. And that comes out to be, I'll throw in my norm signs here, 0.455 meters per second squared. And there we go. That is our problem. All right, so let's just rehash. We have this guy trying to save this little animal from the tree. He's on a spinning fire truck or some kind of truck. And because all these values were constant, that really simplified our analysis as far as the acceleration was concerned. Velocity was more or less just kind of plug and chug. Essentially, once we realized that the angular velocity omega was our theta dot, we just plugged in values. Acceleration got a little bit more difficult, but as long as we just remembered to use the product rule and to be careful with how we differentiated and distributed correctly, again, it was just plug and chug. So yeah, that's all I got for this problem. I hope this was helpful, and if you have any comments or concerns, please post them down below. Otherwise, I wish you good luck with your future problems, and I hope this video was helpful and hope you stick around for the next one. Thank you.